This is the first part of your video for week 9. This is section 5.1, talking about the fundamental identities. So first of all, when we talk about an identity is just an equation that's satisfied by every value in the domain of its variable. Another way to say this is it's something that's always true. We've talked in earlier units about a lot of these identities. We're going to go back over them because we're going to be using them a lot in this chapter. So first of all, the Pythagorean identities. The biggest one is that sine squared theta plus cosine squared theta equals 1. Then we have tangent squared theta plus 1 equals secant squared theta. And cotangent squared theta plus 1 equals cosecant squared theta. And while we're talking about these, for right now I'm using theta as the variable, but it doesn't matter what the variable is as long as it's the same in any place that the variable shows up. For example, this could be sine squared x plus cosine squared x equals 1. It could be a y, it could be an a or b. The next ones are the reciprocal identities. And we just have these three. This is because in this chapter we're going to be doing a lot with rewriting things in terms of sine and cosine. So we just have the three cofunctions, and we want to look at the reciprocal identities for these three. Secant of theta is 1 over cosine, cosecant of theta is 1 over sine theta, and cotangent of theta is 1 over tangent of theta. And then we have the quotient identities. This is another set of identities that we're going to use to rewrite things in terms of sine and cosine. Tangent of theta is sine of theta over cosine of theta, and cotangent of theta is cosine of theta over sine of theta. But these identities we've looked at a lot. Next are some other ones that we haven't talked about quite as much. We did talk about these when we talked about graphing our trig functions, and we talked in terms of whether these functions are odd or even. The only ones that were even functions were cosine and secant. An even function means that if you substitute the negative value of variable, the function being even just takes off the negative. Cosine of negative theta is the same as cosine of theta, and secant of negative theta is the same as secant of theta. The other 4 trig functions are all odd functions. What that means is that the negative doesn't come off, but you can actually pull it outside of the function. So for each of these, we can pull the negative outside of the function. For example, sine of negative theta is the same as negative sine of theta. And it's the same thing for the other 4 of these. Another thing that we'll be using a lot is alternate forms of identities. If we take one of these identities up here and solve it for a specific term, we can get an alternate form of the identity, and that's something that we might want to use in different places. Let's look at an example of this. If we take our basic Pythagorean identity, sine squared of theta plus cosine of squared of theta equals 1, let's say that we want to solve it for sine squared theta. We could do that by subtracting cosine of squared of theta from both sides. That would give us sine squared theta equals 1 minus cosine squared theta. This would be an alternate form of this identity. We could also solve this for cosine squared theta by subtracting sine squared theta from both sides. That would give us cosine squared theta equals 1 minus sine squared theta. When we're talking about identities, these are things that you want to be looking for is alternate forms of these identities. If you see something, for example, that has 1 minus sine squared theta, be thinking about the fact that that's the same as cosine squared of theta. Another thing you might run into is the opposites of these. For example, the opposite of sine squared theta, we could get from here just by multiplying everything by -1. That would give us negative sine squared theta on this side equals -1 plus cosine squared theta. Or we could rewrite this as cosine squared theta minus 1. We could do the same thing with this identity for cosine squared of theta. Let's look at some more examples of this. Let's take another Pythagorean identity, tangent squared theta plus 1 equals secant squared theta, and solve it for two different things to get alternate forms. For the first part of this, we're asked to solve this for tangent squared of theta. All we have to do for that is subtract 1 from each side. That gives us tangent squared theta equals secant squared theta minus 1. And there's an alternate form of that identity. The next part is asking us to take this identity and actually solve it for 1. That means we want to have 1 by itself on this side. To do that, we would subtract this term from both sides. That would give us 1 equals secant squared theta minus tangent squared theta. Here's another example of something that we'll be doing a lot. If we have an expression like this, we might want to rewrite it in terms of just sine theta and cosine theta. We'll go back to those identities and use specific ones to rewrite different things in terms of sine and cosine. For cosecant, we would use the reciprocal identity. Using that, cosecant of theta is the same as 1 over sine theta. Cosine of theta, I'm writing it over 1 because we're going to end up with 3 different expressions that we're multiplying together. And tangent of theta, to rewrite that one, we would use a quotient identity. That says that tangent of theta is the same as sine theta over cosine theta. So for this one, I use the reciprocal identity. For this one, I used a quotient identity. Now that I've rewritten everything in terms of sine and cosine, now I can do some things to simplify. I'm thinking of these 3 terms being multiplied together on the top and these 3 on the bottom, so I have some matching factors between the top and the bottom. I have a sine theta both places, I can cancel those out, and I have a cosine theta both places, so I can cancel those out. That leaves me with just a 1 on the top and a 1 on the bottom, and that simplifies to just 1. Here's another expression that we want to try and simplify. And kind of a rule of thumb with these is that if you see one of your trig functions squared, think of the Pythagorean identities and think of some of those alternate forms we looked at. If we're trying to simplify 1 plus tangent squared theta, that's actually one of the original forms of one of our Pythagorean identities. This would just be equal to secant squared of theta. If we look at the one on the bottom, though, this is an alternate form of that same Pythagorean identity. It's actually one of the ones that we came up with up here. Secant squared of theta minus 1 is the same as tangent squared of theta. So in place of all of this, we're going to put in tangent squared theta. That gives us secant squared theta on the top and tangent squared theta on the bottom. Now, another thing that we could do with this, if we're still trying to simplify, is that we could rewrite each of these in terms of sine and cosine. Our reciprocal identities and our quotient identities just deal with the functions, not the functions squared. But we can still use these. For example, if secant of theta is equal to 1 over cosine theta, that also means that secant squared theta would equal 1 over cosine squared theta. So we're just squaring both pieces of this. We're going to rewrite secant squared theta as 1 over cosine squared theta. And then the same thing with the tangent squared theta and that quotient identity. If tangent is sine over cosine, then tangent squared would be sine squared theta over cosine squared theta. Now we've got the whole thing rewritten in terms of sine and cosine. Now what we would want to do is simplify this rational expression, so we can take the bottom of this and flip it, and that will turn this into multiplication. Now we have 1 over cosine squared theta times cosine squared over sine squared. Now we're simplifying our rational expression by canceling. We have a cosine squared on the top and the bottom. We can cancel those two. That leaves us with 1 over sine squared theta. Now to rewrite this as simply as possible, we can go back to one of our reciprocal identities. It says that 1 over sine theta is equal to cosecant theta. So 1 over sine squared would equal cosecant squared theta. This is as simple as we could get that expression to be. One more way that we can use these identities is to find values of the trig functions if we only have the value of one of our trig functions. In this problem, we only know the value of cotangent of theta, and we know which quadrant theta is in. So let's go back and look at our identities and see which ones involve cotangent. So one of them that involves cotangent is one of our reciprocal identities that says that tangent of theta is equal to 1 over cotangent of theta. That could be useful because that way we could get tangent of theta right away. Another one of our identities that involves cotangent is one of the Pythagorean identities that says that cotangent squared theta plus 1 is equal to cosecant squared theta. Let's use this one first so that we can get the value for tangent. This is going to be easy. All we're doing is substituting in the value that we're given for cotangent, and then we're just going to simplify this rational expression by inverting and multiplying. In other words, we're going to take this and just flip it over. That's going to give us negative 3/5. So there's a value for one of our trig functions already. Now with just cotangent and tangent, we can't go any further unless we use one of the Pythagorean identities. We're going to use this one. And remember, with the exponents, we can rewrite these with the exponent on the outside. That makes it a little bit easier when we're trying to substitute in values. So now we're going to substitute in negative 5/3 for the cotangent. We're going to solve this first for cosecant squared, and then we'll take the square root of both sides, and then we'll have to figure out whether it's negative or positive. Negative 5/3 squared would give us 25 over 9. If we add these together, we get 34 over 9. Now we want to take the square root of both sides. When we do this, we have to look at what quadrant our angle is in. It's in quadrant 2. In quadrant 2, sine and cosecant are both positive. That means when we take our square root, we're just taking the positive square root. Then we can simplify this to the square root of 34 over 3. There's our value for cosecant. Now we've got three of our functions. We have cotangent, tangent, and cosecant. We still need to find the values for sine of theta, cosine of theta, and secant of theta. Sine of theta should be easy since it's the reciprocal of cosecant. For this one, we're just going to take our value for cosecant and flip it over to get our value for sine. For this one, if we wanted to, we could rationalize the denominator. There's our value for sine. We still need to get cosine and secant. To do this, we could use a couple of different identities. We could use the Pythagorean identity with sine and cosine, or we could use a quotient identity. Since we know tangent, we could use this one. Tangent is sine over cosine. Since we know both tangent and sine, we could use that and solve it for cosine. We can plug in the negative 3/5 for tangent and 3 over the square root of 34 for sine. Then we're solving this for cosine. If we multiply both sides by cosine, then we're dividing both sides by negative 3/5, which is the same as multiplying both sides by negative 5/3. The 3's will cancel, and we end up with negative 5 over the square root of 34. There's our value for cosine. Then the very last one that we need is secant. We can use the reciprocal identity and just flip this over to get secant.